In this video lecture, we're going to take everything we did in the last lecture and ask if we can generalize it to an arbitrary number of sets. So here's our new notation. Our sets, instead of just writing A, B, C, capital letters there, we'll write A1, A2, A3, A4, etc. And they're all subsets, just as before, of some universe U. We're going to define these quantities that will make our computations easier. S naught will be, we can think of it as the sum of none of the sets. It's going to be the size of our universe. S naught is how big the universe is. And remember, we should always choose a universe where these things are things we can compute relatively easily. S1 will mean the sizes of the sets taken one at a time. So we want the size of set A1 plus the size of set A2, etc. S2 will be the sizes of the sets taken two at a time. In other words, we'll look at the intersection A1 intersect A2, which we'll write like this, and ask how big is that? And we'll have the intersection A1, A3, and we'll have the intersection A2, A3, and we'll have the intersection A1, A4. And I'll just write, we take the sizes of the intersections of all pairs of sets. So here's a question for you guys. What if I have exactly n sets? So what if the sets are A1, A2, A3, A4 up to, and then there's a last set here, say A sub n. I have exactly n sets. Well, then there'll be just the one thing in S naught. There'll be then n terms in S1. It'll be the sum of the sizes of the n sets. How many terms will there be when you compute S2? Well, we want to add up the sizes of the intersections of all pairs of sets. How many pairs of sets will there be? There will be exactly n choose 2 pairs of sets. So there'll be n choose 2 terms here in this sum. Well, what will we mean by S3? Well, we'll take all triples of sets, for example, A1, A2, A3, and we'll look at that intersection and we'll ask how big is that? And they'll add up A1, A2, A4, for example, and they'll add up over all triples. How many triples are there of sets? Well, there'll be exactly n choose 3 terms. Because if they're n sets total and you take them in groups of 3, you have exactly n choose 3 of those, and we're going to look at the size of each and every one and add them up, and that's what we'll call S3. And then we'll keep going like that. S4 will be the same thing, where you sum up the sizes of the intersections of each group of 4 of the sets, and there'll be n choose 4 terms. And we can keep going like that as far as necessary. Oops. I'll let that one get away from me. Okay. With those definitions now, we can get inclusion-exclusion formulas for the union of the sets A1 through AN. And I'll tell you how that formula works. It's just like what we saw at the beginning. You start with S1. That's the size of A1 plus the size of A2 plus the size of A3, etc., all the way up to the size of AN. In other words, we add up the size of all the sets. The problem is, of course, many things are double counted. Anything in an intersection of two sets is double counted, so we're going to subtract the sizes of all the intersections. But anything which was in 3 or more of the sets has been now totally removed, so we have to put that back in. We add the sizes of the intersections of the sets 3 at a time. But then we subtract S4, and then we add S5, and we keep going, and we end up with S sub n. I put plus or minus because you see if n is odd, you'll get a plus. If n is even, you'll get a minus there at the end. We just keep including things and excluding things, and including them and excluding them. And if we keep going, we'll get every element the correct number of times. We'll see that in a future video lecture, why that works perfectly. Now, it's often going to be interesting for us to compute the size of the intersection of the complements of sets. And we'll see that's very similar to the union of the sets, because by De Morgan's laws, the intersection A1 prime, A2 prime through AN prime is exactly the complement of A1 union A2 union A sub n. So if we can count the union, we can count the intersection of the complements just by taking S naught, remember that's the size of the universe, and subtracting the size of the union, which is S1 minus S2 plus S3 minus S4, etc. So we're going to get S naught minus S1, then plus S2 minus S3. These signs are just flipped from the way the signs were up here. And again, we'll end up, I'll write minus or plus Sn. It'll be a minus sign now if n is odd, and a plus sign if n is even. These will be our general inclusion-exclusion formulas that we can use when we have some arbitrary number of sets, n sets, involved. When we have a problem, our goal will be to be able to apply one of these formulas. Let's see as an example counting derangements. We saw that that was a pretty tricky thing when we first looked at derangements. Our question now is, what is D5? In other words, how many derangements are there of the string 1, 2, 3, 4, 5? Well, we want to set up our notation so we can use the inclusion-exclusion formulas that we just derived in the last slide. First, we'll define the universe and our sets. Our universe will be the set. Always try to use that word. The universe is the set of all rearrangements of the string 1, 2, 3, 4, 5. Is that something we can count easily? I hope so. The size of that universe is exactly 5 factorial, which is 120. That's all rearrangements. Many of them, of course, are not derangements, but there are 5 factorial rearrangements of the string. What are the sets A, B, C, D, and E? Well, I'm going to define A to be those rearrangements that fix the number 1. When I say fix the number 1, that means leave the number 1 in its original position. They start with the 1. Here's an example. 1, 3, 2, 5, 4. That's a rearrangement that fixes the number 1, so that's counted in the set A. The other sets will be defined similarly. B is those rearrangements that fix the number 2. C will be the same thing, the ones that fix the number 3. D will be the same thing, rearrangements that fix the number 4, and E will be the rearrangements that fix the number 5. Here's a question. What are the sizes of these sets? How big is the set A? How many rearrangements leave the number 1 in its original position? Well, if the number 1 is in the original position, I just need to rearrange the other 4 elements in our string, the other 4 letters in our string. There are going to be 4 factorial ways to do that. Similarly, if I fix the number 2, for example, 5, 2, 3, 4, 1, that fixes the number 2. I can do that in 4 factorial ways, just rearrange these numbers 1, 3, 4, and 5 and put them in the other positions. So the size of B, the size of C, the size of D, and the size of E are all 4 factorial. Now, before we continue further, we really have to identify what it is we want to count. We want to count derangements. A derangement means no element is in its original position. Well, if no element is in the original position, that means it's not in set A, it's not in set B, it's not in set C, it's not in set D, and it's not in set E. In other words, it's in A prime, it's in the complement of A, it's in B prime, C prime, D prime, and E prime. And we want to count the size of this, so this is exactly what we want to count. D5, the number of derangements, is exactly the size of this intersection of the complements of the sets. Now, the appropriate inclusion-exclusion formula says we can count this intersection of the complements by starting with S0, subtracting S1, adding S2, subtracting S3, adding S4, subtracting S5. We don't have to go any further. There are only 5 sets. S5 is the size of the intersections taken 5 at a time. There won't be an S6 since we only have 5 sets. Now we already know S0, that's just 5 factorial. S1, remember, is the size of A plus the size of B plus the size of C plus the size of D plus the size of E. That'll be 5 times 4 factorial. But how will we count S2? Well, we might ask, how many terms are there in S2? There are 5 sets, and we're adding up the sizes of the intersections 2 at a time. So it will be a sum of 5 choose 2, which is 10 terms. Each will look like, an example here, the size of AB. They'll be the size of AB, the size of AC, the size of AD, the size of AE, the size of BC, the size of BD, the size of BE, the size of CD, the size of CE, and the size of DE. Those are all 10. I'm not going to write those down now. I claim they're all exactly the same size. Why? Let's look, for example, at this AB. A rearrangement is in AB if it fixes 1 and fixes 2. Well, if it fixes both 1 and 2, the rearrangement just amounts to rearranging the numbers 3, 4, and 5. And there are 3 factorial ways to do that. For any pair of sets that a rearrangement is in, it fixes 2 of the 5 numbers, and you just rearrange the other 3 in 3 factorial ways. So there will be 10 terms, even though those 10 terms are the sizes of different sets. All of those sizes are 3 factorial, so we're going to add in 10 times 3 factorial. And now you see it becomes very easy. S3 is a sum of 5 choose 3, which also is 10 terms. And we're looking at, for example, the size of ABC. A rearrangement is in ABC if it fixes 1, 2, and 3. That just means you can rearrange the elements 4 and 5. That's just 2 factorial ways to do that. And in fact, of all these 10 ways to look at intersections of the sets 3 at a time, those sets will all have size 2 factorial, or just 2, because you only get to rearrange the 2 remaining elements, and that can be done in just 2 factorial, or 2 ways. So the minus S3 would be minus 10, which is 5 choose 3, times 2 factorial, or 2, to get S3. Well, what about S4? That'll be a sum of 5 choose 4, which is only 5 terms. Here's an example, the size of A, B, C, D. How big is A, B, C, D? Well, A, B, C, D means 1, 2, 3, and 4 are all in the original positions. How many ways can that be done? Well, the 5 has to be in its original spot as well, because that's the last spot. So there's only one way to do it for all of those. So we're just going to add in 5, and you'll see for each of the 5 different terms, they'll all be of size 1. There we have it. Then we have to go and subtract A, B, C, D, E. Well, what is A, B, C, D, E? S5. There's only the one term. We want to count rearrangements that fix 1, fix 2, fix 3, fix 4, and fix 5. There'll clearly be just one way to do that. So, and I don't know why I wrote D4. This is counting D5. I apologize for that. D5 are number of derangements of a 5-letter string is just 5 factorial. that's 120, minus 5 times 4 factorial, which is 5 times 4 factorial is the same as 5 factorial, that's 120, plus 10 times 3 factorial, which is 60, minus 10 times 2 factorial, which is 20, plus 5 minus 1. These cancel. We have 40 plus 5 minus 1, which is 44. So we've computed here that the number D5 is precisely 44. There are 44 derangements of the string 1, 2, 3, 4, 5. Now, in coming lectures, we're going to see why this general inclusion-exclusion principle will work and how we can use it in many, many, many more examples.